Hello friends, today we are going to discuss about spatial analysis in urban planning. This is an introduction to GIS, that is Geographic Information System. So let us understand what is GIS. Geographic Information System is a computer system built to capture, store, manage, analyze and display all kind of spatial or geographic data, and all the data is aggregated into a location reference system, that is longitude and latitude of the space. GIS objective: maximize the efficiency of planning and decision-making process in different areas of study. Provide efficient means for data distribution and handling. Elimination of redundant database, minimize duplication and enhance the quality of the data. Capture to integrate information from many sources and integrate in one database. Complex analysis query involving geographic reference data to generate new information for taking actions to improve the quality of life and living standards. So GIS is a computer-based hardware, then it is operated through software. We input data through people, and this GIS was developed by Dr. Roger Tomlinson in 1962, who was working in Canadian Geographic Information System (CGIS) for the Canada Land Inventory, and that was the first invention of the GIS. Geospatial data format. There are two formats of the data, that is raster and vector. Raster data is viewed as a series of grid cells where each cell has a value representing the feature being observed, best suited for continuous data or information that does not have hard boundaries or location, that is like elevation, temperature, etc. Vector data. These are represented as either point, line or polygon. Discrete or thematic data is best represented as vector. Data that has an exact location or hard boundaries are typically shown as vector data, like administrative boundaries, road, bus stop, and others. Raster data format. ArcInfo grid, composed of two folders within a workspace with each contain multiple files. Folder carries the name of grid and contain a number of various like .adf files. Multi-band image format like band interleaved by line BIL format, band interleaved by pixel BIP format, and band sequential BSQ. DEM, Digital Elevation Model. DEM is a raster format used by the USGS to record elevation of the point on Earth's surface. GeoTIFF. This raster image includes geographic extent as a part of the header information of the TIF, tagged image file format. Other popular raster data format are ADRG, Arc Digitized Raster Graphic, RPF Raster Product Format, DRG Digital Raster Graphic, ECRG Enhanced Compressed Arc Raster Graphic, ECW Enhanced Compressed Wavelength, EDS में यूज होता है ये, ESRI Grid, ASCII Raster Format used by ESRI, GeoTIFF TIFF variant enriched with GIS relevant metadata, HDF hierarchical data format files, IMG image file format used by ADAS, JPG 200 Joint Photographic Expert Group Committee using discrete wavelength, Transform DWT, Best Compression Standard, MR Mr. SID, MRSID, Multi-Resolution Seamless Image Database. So these are the other type of raster data format that are used in GIS. and other applications. Vector data format. Vector data format is called shapefile, which is compatible with most of the GIS software such as .shp, which is shapefile, .shx header file, .dbf associate database file, .prj projection file, and .lyr layer file. ArcInfo coverage replaced nowadays by geodatabase format, composed of two folders within a workspace. First folder is the name of the coverage and contain a number of various .adf files. Info folder contain .dat file and .nit files for all the coverage and grid in the workspace. GeoDatabase native data format for ISRI ArcGIS. Collection of geographic data set of various types like basic type being vector, raster, and tabular data. Light detection and ranging LiDAR pulsed laser to measure ranges, variable distances to feature objects. Point cloud data has .las file extension. Other popular vector data format are AutoCAD DXF, AutoCAD DXF format by Autodesk, Cartesian Coordinate System XYZ Simple Point Cloud, DLG Digital Line Graph USGS format, DML Geographic Markup Language OpenGIS format used for exchanging GIS data, GeoJSON, a lightweight format based on JSON used by many open source GIS packages, GeoMedia Intergraph Microsoft Access based format for spatial vector storage, ISFC Intergraph MicroStation based CAD solution, Keyhole Markup Language KML. KML markup language is XML based, which is used in Google Map. MapInfo tab format, MapInfo vector data, NTF National Transfer format. Spatial Light is a spatial extension of SQLite. Simple features like specifications for vector data. SOSI, a spatial data format used for all public exchange of spatial data in Norway. Spatial data file like Autodesk high performance geodatabase format. Tiger, topographically interrelated integrated geographic encoding and referencing. So Tiger file format, VPF vector product format. These are different format of the vector data. So what are the uses of GIS? GIS is used for location of features in relationship to each other, assessing the intensity of the feature, mapping quantities like population distribution, distribution of density of population, distribution of services, assessing the density of features like population density, monitoring temporal change like urban sprawl, monitoring status in an area of interest like flood damage assessment, list of villages inundated, proximal studies like finding land use along different road segments using buffering, modeling and simulating complex scenarios like air pollution due to locating an industry or area prone to seismic hazards. Map projections like the type of map projections. Earth is a curve and map are flats. Mathematical process of flattening Earth 3D surface onto 2D map surface. This process will always have a distortions, which includes conformity, accuracy of shape of the map, distance, accuracy of measured distance on the map to the actual distance on the Earth. Area represented on the map is proportional to the actual area on the Earth. Directions between points on the Earth's surface is accurately represented on the map. Geometric transformation, map projections and transformations like projectional and coordinate transformation. So Earth is like a geoid. It is not a round. So map projections can be transformed like scaling, shearing, rotation, flipping, translation, and then finally we have transformed image. Geometric transformation is the process of using a set of control points and transformation equation to register a digital map, a satellite image, or an aerial photograph onto a projected coordinate system. Map-to-map transformation, digitized map, either manually digitized or traced from a scanned file into a projected coordinate. Image-to-map transformation applies to remotely sensed data. Transformation changes the rows and column of satellite image into a projected coordinates. Geometric transformations uses a set of control points to establish a mathematical model that relates the map coordinate onto one system to another, or image coordinate to map coordinate. Transformations methods like equal area allow rotation of the rectangle and preserve its shape and edge size. Equal area. Similarity transformation allows rotation of the rectangle and preserve its shape but not size. Affine transforms allow angular distortion of the rectangle but preserves the parallelism of lines. Parallel lines remain as parallel lines. And projective transformation allow both angular and length distortion, thus allowing the rectangle to be transformed into an irregular quadrilateral. Affine transformations, differential scaling, rotation, skew, and translation. These are the four methods through which we can do affine transformation. So affine transformation update control point to the real world coordinate, run affine transformation on control point, and apply affine transformation to map features. This is the most commonly used transformation of the image in the GIS platform. And second is the control point. Control points play a key important role in determining the accuracy of affine transformations that transforms the image or satellite imagery taken or from the different sources of the images on a GIS platform. Control point for map-to-map transformation can be done using the known latitude and longitude of a place, which is of selected points, and then the real ground data is then input in the map, and then we can project the coordinate in the real world coordinate. Control points for image-to-image transformations are used where both image coordinate and the real world coordinate can be identified. After ground control points are identified on a satellite image, their real-world coordinate can be obtained from digital maps like GPS, Global Positioning System, or other software. Basic vector data types are like point features, made of a point or set of points like bus stop, schools, location of hospitals, location of dustbins, guards. It depends on the scale. When we talk about the larger scale, then a building can become a point. But when we come to a smaller scale, then the building will be a polygon line, one-dimensional, and that has the property of length in addition to location, has two endpoints and may have additional point in between to mark the shape of the line. Shape of the line may be connection of the straight line segments or a smooth curve generated using a mathematical function. Line feature is made of a line or a set of lines, that is like road, boundaries, or small streams or natural streams, drainage lines, and others. Polygon, two-dimensional, and has the properties of area, size, and perimeter in addition to the location, made up of connected, closed, non-intersecting lines. The perimeter or the boundary defines the area of the polygon, may stand alone or share boundaries with other polygons, may also have a hole within its extent resulting in exterior or an interior boundary. Polygon features consist of polygon or a set of polygons. Example like when we digitize the buildings, when we digitize the vegetated area or urban area and water bodies, then we get different type of polygons. Vector data like point, line, and polygon. Here we can see the example how it is represented and how the data set is generated. Topology. Properties of geometric objects that remain invariant under certain transformations such as bending or stretching can be explained through directed graphs diagram which shows the arrangement of geometric object and relationship among objects. Adjacency and incidence are two fundamental relationships that can be established between nodes and arcs in a diagram. Topology requires additional data file to store the spatial relationship. Topological relationship between spatial features allow GIS users to perform spatial query. Containment and intersects are two of the topological relationship that is important for data queries. GeoRelational data model store geometric and attributes separately in a split system like geometry geo in graphical file or spatial subsystems and attribute relational in a relational database. Use the feature identification number ID to link the two components. Two components are synchronized so that they can be queried, analyzed, and displayed in a unison manner like the coverage and the shape file. Coverage is the topological and the shape file is a non-topological. ArcInfo coverage has two components, graphic file for spatial data and info file for attribute data. The level contains the two components. So this is the graphical file and this is the info file. GeoRelational coverage. Coverage supports the three basic topological relationships. Connectivity, arc connect to each other at node. Area definition, an area is defined by a series of connected arcs. Contiguity, arcs have directions left and right polygons. The starting point of an arc is from the node and the end point is to node. So here we can see from this image how this three component of the coverage, connectivity, area definition, and continuity arc are shown here. Shape file. Standard non-topological data format used in ISRI product like shape file treat a point as a pair of XY coordinate and a line is a series of points. Polygon is a series of line segment. A spatial relationship among these geometric objects are not described in any file. Polygon actually have duplicate arc for shared boundaries and can overlap over one another. So the advantage of using shape file, they can display more rapidly on computer monitor, non-proprietary and interoperable. Interoperability like Open Geospatial Consortium was signed in 1994, which enhances the interchange of data from one system to another. .shp file stores the feature geometry and .shx files maintain the spatial index of the feature geometry. Object-based data model. GIS operations are affected by property describing the attribute or characteristics of the object like shape, extent, methods like performing a specific action like copy or delete. A standard non-topological data format used in ISRI product stores geometric and attribute in a single system. Geometries are stored as a collection of binary data in a special field with data type blob, binary large object. Spatial features like object to be associated with a set of properties and methods. So polygon object ID is created and then polygon is drawn, then we create some numerical ID like land use ID, then we define some category, then the shape has some length and shape will have some area. GeoDatabase uses point, polygon, polyline and polygon to represent vector base, similar to arc coverage in a simple feature, differs in the composite feature of region and route. GeoDatabase can also store raster data, triangulated irregular network, locational data, and attribute tables. GeoDatabase organizes vector data sets into feature class and feature data sets. So what are feature class and feature data sets? The feature class stores spatial feature of the same geometry type, participate in topological relationship with one another, that is coincident boundaries between different level of the census data like village, taluka, block, district, state, and country. But feature data sets stores classes that share the same coordinate system and area extent. So feature class will be unit data and the data set will be collection or store of the feature classes. Triangulated irregular network TIN approximate the terrain with a set of non-overlapping triangles. Each triangle in a TIN assumes a constant gradient. Each node of the triangle is a point and each edge of the triangle is a line. Data structure therefore include the triangle number, the number of each adjacent triangles, and data files showing the list of point edges as well as XYZ value of each elevation points. So this triangulated irregular network TIN model is used to represent the digital elevation model of a place. Region: set of geographical area with similar characteristics are called region. Two or more regions can cover or overlap the same area. We can see that the example, the geologically prone area or fragile area can contain riverbed as well as forest land, but these two can also be another region like forest region and water body. So though if we call geologically prone area, then both will come in one region. Regions are organized as subclasses in polygon coverage. Additional data file regions are related to the underlying polygons and arcs. So there is a hierarchy of administrative units which are shown in this map. Routes: linear feature stored as a subclass in a line coverage collection of sections. It has a from position FPOS and a to position TPOS. It has a from feature F means beginning point of the route and a to measure T means. Both the shapefile and geodatabase use polyline with M feature value to replace route subclass for GIS applications. Route is shown here as a thicker gray line is built on a polyline with linear measure in geodatabase. Raster data. Advantage of using raster data: better option for representing continuous phenomena like the vegetation, land use of the area, regional land use, land cover. Also called the field-based model, uses regular grid to cover the shape. Value in each grid cell correspond to the characteristics of a spatial phenomena at the cell location. Changes in cell value reflect the spatial variations of the phenomena. Examples: digital elevation data, satellite image, digital orthophotos, scan maps, and graphic files. These are all forms of raster data. Require large amount of computer memory for storing raster data. Much easier to use, aggregate, and analyze than vector data. Raster and vector data complement each other. While vector data is easy to handle in computer systems, whereas raster data is more handy to use in daily life. Raster data element, also called a grid or an image in GIS, divided into row, column and cells called pixels with images. Origin of rows and column is typically at the upper left corner of the raster. Rows functions is y coordinate and columns is the x coordinate. Matrix with row and column and will cell value will be stored or in a two-dimensional array. Each cell in the raster is explicitly defined by its rows and column position. Representation of point, line, polygon features in the raster as well as vector is shown here. So we can see that how in both the file format we can see the differences. So raster data structures. Method for encoding, storage, processing and display of spatial raster data. So cell by cell encoding, run length encoding and quadtree are three processes through which data is encoded, stored or processed for display in the spatial format. So cell by cell encoding, exhaustive enumeration, simpler raster data structure functioning at the cell level. Ideal choice if the cell value of a raster change continuously. For example, DEM as a neighboring elevation value are rarely the same. Stored is a matrix or cell values are written into file by rows and column. Satellite images are also encoded cell by cell. Satellite images have multiple spectral band and has more than one value for each pixel. Data is stored in this format like PIP, BIL and BSQ format. Band interleaved pixel allows fairly easy access to both spatial and spectral information. Red value for the first pixel is written to the file, followed by the green value for that pixel, followed by the blue value for that pixel, and so on for all the pixels in the image. So this is an example of PIP file format. So this is the image data and this is the cell by cell encoding data. Band interleaved line. All the red values of the first row of the pixel are written to the file, followed by all the green value for the row, followed by all the blue value for that rows, and so on for every row of pixel in the image. So this is continuous process and interleaved line. Band sequential. All the red values for the entire image are written to the file, followed by all the green values for the entire image, followed by all the blue values for the entire image is written. So this is called band sequential encoding. Run length encoding. Useful when raster contain many redundant cell value or repetitive cell value. RLE run length encoding method records the cell value by rows and by grouping having the same cell value. RLE method for encoding as well as compress is raster data. Software utilizing cell by cell encoding for storing raster data are like GRASS, Idrisi and ArcGIS. Row 1 has two addition gray cell in column 5 and 6 and row 1 therefore encoded with one beginning in column 5 and ending in column 7. So this here this data has been represented here. Quadritree encoding uses its recursive decomposition to divide a raster into hierarchy of quadrants. Recursive decomposition continuous subdivision until every quadrant is a quadritree containing only one cell value. Quadritree contain nodes and branches, that is called subdivisions also. Node represent a quadrant. Depending on the cell value in the quadrant, a node can be node leaf represent a quadrant that has different cell value. Branch point meaning that the quadrant is subjected to subdivision. Leaf node represent a quadrant that has same cell value. It is an end point which can be coded with the value of the homogeneous quadrant gray and white. Quadratary encoding is a depth of quadratary or level of hierarchy vary depending on the complexity of the two-dimensional feature. Spatial indexing. After completion of the subdivision, next step is to code the two-dimensional features in binary format. Quadratary code for given image can be seen here. So this is the spatial indexed 0 for northwest, 1 for southwest, and 2 for southeast, and 3 for northeast. Quadratary code can be 0 to 032. So this is written here. This 0, this is 1, this is 2, this is 3. So we have null leaf node shown by a square, gray leaf shown by gray dot, and white leaf by blank circle. Now we will discuss about data compression. So there is two format of data compression. There is lossless and lossy compression. Lossless preserves the cell or pixel value. Original image can be exactly recreated. Desirable for raster data that are used for analysis. RLA, LZW, Limpel, GWelch. For lossy compression cannot be reconstructed fully. Original image can achieve higher compression ratio compared to a lossless compression. Useful for background image rather than using it for analysis. For example, MRSID multi-resolution seamless image database, JPG 2000 ECW enhanced compressed wavelet using HAR function. Wavelet transformations can be done using image compression technique. Treat an image as wave, progressively decompose the wave into simpler wavelet. Thank you for discussion.